Learning Measure TV, a science and engineering podcast with emphasis on measurement, brought to you by David Archer and LearningMeasure.com. Episode 21, Music to the Ear. Hello, I'm David Archer, owner of LearningMeasure.com and LearningMeasure.tv. If you looked at the website recently, you'll notice that we've made some changes. We have a new logo for LearningMeasure.com and LearningMeasure.tv. And now we're going to say a little bit news about what's going on with LearningMeasure.com. LearningMeasure.com is a subscription-based website that's associated with this podcast. And when you register with LearningMeasure.com as a student account, you get 2 weeks of free. And after that, it's $5 a month to maintain your subscription. With your subscription, you have access to all our course materials and other materials that requires registration. I'd like to announce a new course that just got put into the course catalog, Measurement 110, Basic Measurement Concepts. This is a follow-on to Measure 101, Introduction to Measurement Concepts, and it's just going further into descriptions of various different concepts used in measurement. Okay, now I'm going to start out with a little review of what we did in the last couple episodes. In the first 2 episodes ago, we talked about integration, of a function, which is as fancy. The sign here is an S, an elongated S, means some sort of sum. Integral of some function f of x dx is defined as, basically one way of defining it is limit is you break it into bunches of chunks of f of a plus b minus a over n I times b minus a over n. So in other words, if you have some function like this, the area is under the curve, let's say A to B, which is what this represents, can be thought of the limit as a bunch of rectangles, n rectangles. So, and then you just sum all these rectangles up and you get an approximate area. Well, last week we talked a little bit about vectors. Seemingly unrelated subject, where you can describe a vector by its components in an orthonormal basis. For instance, in 3 space, or let's say 2 space, you might have 2 vectors, x hat and y hat, unit vectors. Any vector at all, let's say A, is going to be some component times x hat plus some component times y hat. And the way you get these components, A is equal to, we talked about the dot product, A is equal to A dot x hat, and B equals A dot y hat. So you get the components of a vector by taking the dot product of the vector with the unit vector for that particular coordinate system, the basis for that coordinate system. Well, and then we went on to say, well, in other words, in n dimensions, we went from like 2 all right away to n dimensions. Similarly, in n dimensions, let's say you have a vector A in n dimensions. It's going to equal the sum I equals 1 to n of A dot, we're going to call E I hat as the vector for the ith direction. So this is starting to look like this. Well, in fact, one could conceivably call these, these n-dimensional vectors, or maybe infinite dimensional vectors, as a particular type of dot product in particular. But we're going to change notation here a little bit, because functions we're going to talk about taking inner products or dot products of functions. And it would get confusing if you did f of x dot y of x, because we don't know if that's multiplication, composition, whatever else, that we don't know what that is. So I'm going to create a new notation now. I'm going to use a little slightly different notation. We're going to say for vector A dot a vector B, we're going to change the notation to be this way. We're going to change the notation. An object like this is called a ket. An object like this is called a bra. And together they form a bracket or bracket. Okay, that's just what the notation is. So we're just going to say this is A dot B, or this is the inner product of A and B. Well, this thing you might be able to say is the integral from A to B of f of x dx. I mean, you could, on that interval, define an inner product on that interval A, B, and this is just sort of the inner product of a function with 1, like the function 1. Okay. So, well, yeah, but what does that do for you? Like we said before, in vectors, if A dot B equals 0, they're called orthogonal vectors. If two functions, f of x and g of x, have an inner product that's 0, we call them orthogonal functions. Just like in a vector, the magnitude of a vector, we'll call it the magnitude of, is the square root of A dot A. Well, we're going to do the same thing here. We're going to call the magnitude of the function, this is, well, can't use that symbol. We're going to use some other symbol. We're going to put 2 lines here because we don't want to get that confused with absolute value. The symbol was called the norm. So this is going to equal f of x, the inner product of x with itself, square root. As you can probably see already, these are completely identical definitions. Okay, we could say that the magnitude of the vector A, using this notation, is the square root of the inner product of A with itself. Okay. So just like you can normalize a vector, let's say you want A hat, well, let's call it A hat, being the vector A divided by the magnitude of A. Okay, that's a unit vector in the direction of A. You can normalize a function too. This would be a normalized function whose inner product's 1. You can do the same thing. Let's say, well, we'll have to come up with some different. Let's say we have some function f of x, capital F of x. Normalized function f of x is equal to f of x divided by, well, the magnitude or the norm of f of x. So in exactly the same way that you can have an orthonormal basis in vector space that we talked about last week, you could create an orthonormal basis in this function space. All you need is a bunch of functions, orthogonal functions, properly normalized, and you have an orthonormal basis. Well, what are examples of orthogonal functions? It turns out, we're not going to go into that here because we don't have lots of time. Examples of orthogonal functions are things like sines, cosines, complex exponentials. Those are all examples of orthogonal functions like sine omega x, sine ei omega x. These are all orthogonal functions. Other examples are Bessel functions, Legendre polynomials. There's all kinds of orthogonal functions. But in particular, these, the complex exponentials or the sines and cosines, in general, what they call sinusoids, are a special type of orthogonal basis. In fact, what you can do then is create this inner product, let's say any arbitrary function on some interval. If you take the inner product with a complex exponential properly normalized, this isn't normalized right. There's going to be some constant here, normalization constant. We don't care what that is at the moment. And then you multiply it by e to the, basically, minus I omega t, let's say x or t, it doesn't matter. That gives the component, that gives the component of this function that's that part of that in the direction of that particular function. So if you have, a of omega equals f of x, the inner product with some properly normalized complex exponential, this particular thing is basically called the spectrum, the amplitude spectrum of the function. Now, you may have heard the term spectrum before, like in spectrum analyzer or frequency spectrum. That's what this is. Okay, so this is going to be some sort of constant times an integral over some interval, usually minus infinity to infinity, of some function times e to the I omega x dx, or dt, whatever. This is going to be a of omega. This is a particular thing. Usually you put minus infinity to infinity. I'll just do that. This function here is called the Fourier transform of this function. Okay, this gives you the spectrum. All that means is at this particular frequency, this much contributes to the overall waveform. So if you had something that was tuned to, like a filter that was tuned to a particular frequency and you had some arbitrary signal coming by, this will give you how much response you're going to get out of that filter. Basically, what's called convoluted with the filter, but that's besides the point. So basically you can think of this, a of omega times e to, let's say, for some reason I'll put a minus here. This will get you back the original function. So you're basically summing up each of the components in that basis to come back to the original function. Exactly in the same way that a vector A in 2 dimensions can be, or n dimensions can be written as the sum of its components times the basis vector plus a component times another basis vector. This is just an infinite number of components in this basis. Now there is this normalization constant up front that's a little bit of an issue. There are several different ways, conventions to use for the normalization constant in this particular case of the Fourier transform. Between the two, there has to be, normally there's two, you put 1 over the square root of 2 pi is the normalization constant if you want the Fourier transform and the inverse Fourier transform to be symmetric. Between the two of them, you have to have a factor of 1 over 2 pi to come back to the original function. So sometimes you'll see 1 over the square root of 2 pi normalization in Fourier transform. Sometimes you'll see 1 over 2 pi on one and 1 on the other. Doesn't really matter, or you can break it up however you want. You'll get the same result. Anyway, so that gives you the spectrum. And your ear does something like this. Your ear is a bunch of basically filters, different, the hairs in your ears. They respond to different frequencies. So your brain, you get basically some component, electrical signal is proportional to the intensity of that particular frequency, and your brain does this operation of summing things up to come up with the sound you hear. So this is sort of an abstract mathematics for a very physical thing. The square of this is called the absolute square of this. It's called the power spectrum. And really, that's what most spectrum analyzers, or 20 log A omega in many cases, that gives you the spectrum in dB. So but that's just another way of thinking of what a spectrum is. A spectrum is for a particular frequency, what portion of the signal, what fraction of the signal is associated with that frequency. And when you sum up all the frequencies, you end up with the signal, and times the component, you end up with the function you originally had. You may have seen before how you can build up a square wave by adding up sums of sines and cosines. Very similar, exactly, one is a more discrete. You can either do this discrete or continuous. One's called a Fourier transform, the other is called a Fourier series. But in either case, all you're really doing is finding out the components of a particular function with regards to properly normalized sinusoids. And that gives you spectrum. So if you ever had use of a spectrum analyzer, that's all you're doing. You're finding out in a particular signal what portion of the signal can be associated with a particular sine wave. Okay, this was a little bit abstract, but this is basically basic stuff you would measure in electronics with a spectrum analyzer. And it's no different than decomposing a vector into its components. You're decomposing a function in terms of sinusoids. That's all I really wanted to talk about this time. Again, if you have any suggestions about what you'd like to see on the podcast, send us an email at suggestions@learningmeasure.tv. If you have a question, any type of question at all, homework question, any engineering question, personal question, I suppose, and I'll decide whether I want to answer it, send an email at questions@learningmeasure.tv. And if you're a vendor that wants to show your products here or be in an interview or you just want to be on the podcast, send us an email at vendors@learningmeasure.tv. That's it for this time. Next time, I'm hoping we can get an interview. I'm really trying to get somebody here and we'll see. But if not, we'll probably do something with the concept of spectrum. All right, that's it for now. Goodbye.